The work I'm going to do, and I'm doing with my research group, is to make the energy conversion processes of the future reliable, that is important, but as well clean. To start with some background information, I think it's very important to share some facts. Sustainability of energy conversion processes, we know that from everyday newspapers, I think, is one of the most urgent global tasks. And this is reflected, for example, within the European Green Deal or with some of the Sustainable Development Goals of the United Nations, such as goal number 7, which is about affordable and clean energy. Going a little deeper, I would like to share the information you need to understand our vision. It's about the transformation of our energy system. And this comes along with a number of challenges. We have to drastically reduce the emission of greenhouse gases, and as you see, that's true for all sectors: electrical power generation, heat, mobility, industry, buildings. And for that, we need to substitute fossil fuels with energy from renewable sources. The time frame for that is set by the Paris Climate Agreement, and particularly in Germany, by the consensus to phase out from nuclear within the couple of months, and from coal power latest 2038. And the challenge is shown in this view graph you see in the lower left, where you see the emission, the global emission of CO2 in million tons over the last 60 years. It's increasing constantly. We have to change this trend. We have to lower these emissions to those locations marked by these red arrows to meet the goals of the Paris Climate Agreement. And for that, we have to act now. The best approach, however, is not known to us. Mankind has no experience with such a transformation of our energy system. And so this comes along with risk of wrong decisions. And so because of that, my strong belief and opinion is we need technology options from which we can choose during this transition is going on. A little more detail, taking the power generation as example. For the example of Germany in 2020, the annual demand was roughly 550 terawatt hours. This is an integral measure. And to give you an idea what this number means, that corresponds to something like 81,000 times the largest hydropower station we have here. But this is an integral measure. We have to check and look at the capacity profiles. And for the example of December 2019, taking these data, you see the capacity over that month. And this is measured in gigawatt. And you see, color-coded, that we rely so far on an energy mix consisting of some hydropower, limited, biomass, limited, nuclear power to be phased out, then fossil fuels, lignite, black hole, and gas. And you see by this yellow arrow that this need to be replaced by renewables. And the renewables are actually photovoltaics, PV, and wind. And already by the size of this yellow arrow, you see we need massive installations into renewables. However, what you see as well, that is these renewables, which are color-coded by this greenish color for wind and yellow for solar power, they strongly fluctuate. The short dark period you see around the 28th of December of that year, these renewable energies, almost nothing contributed to the net. So the real challenge is we need to compensate this volatility of PV and wind. The volatility can be quantified, it can be measured, and we do that by so-called full load hours. The year has 8,760 hours, and PV contributes, at least here in this country, by less than 1,000 full load hours. Wind onshore is a little better, roughly 1,600, but this needs to be compared to conventional power stations like lignite. A power station operates there typically more than 6,500 hours per year. And this volatility is once again shown in this view graph. You see production of wind and solar. It peaks up to 55 gigawatt, but these are peak loads with installed capacity by that time of the year 2019, which was in the order of 115 gigawatt. So the volatility is brings us to the consequence that we need to install much more than we need. Installed capacity must be much larger than the required power. And now it depends on the scenario, whom you ask. Some of those say we need 600 gigawatt, and this needs to be compared to what we currently have, which is 120. So a factor of 4 to 5. Hard to imagine. So we need as well ideas how to store and transport energy from renewable sources. This is of central importance. Now, how can we store energy? There are different types, of course. I share here a classification showing the discharge duration and the storage capacity. I guide you through this view graph. The storage capacity goes from below 1 kilowatt hour up to a number of terawatt hours. Between 1 kilowatt and 1 terawatt hour, this is a factor of 10 to the 9, a factor of billion. To give you again some idea of what these numbers mean, a few megawatt hours is what typically a two-person household in this country would need. If we're talking about a couple of terawatt hours, we can supply a large city. The discharge duration spans from a millisecond to a year. And it gives a number that quantifies for how long you can extract energy from an energy storage device at full power. For example, electrical devices shown in blue, coils, capacitors, they provide energy in the order of a few kilowatt hours for minutes. In green, electrochemical devices, lithium-ion batteries, a few megawatt hours, maybe up to a day. If you want to supply urban areas, if you want to supply industrialized regions, you need much more. So we're talking about the terawatt hour regime, and we need to supply that over long periods. And this brings up to the upper right, shown in reddish color. These are chemical energy carriers. Chemical energy carriers can be produced from renewable sources. And so these type of chemical energy carriers, actually not fossil, but produced from these renewable energies, those will be irreplaceable in the future. We will not be able, that's my prediction, to produce these energy carriers here in this country on our own. So what we need is a global trade of these energy carriers, but produced in a sustainable way. And this is to replace the kind of trade we have with fossil fuels. Let's come back about the production. You see there power to gas. Maybe the most popular chemical energy carrier we're talking about these days is green hydrogen. It's a very good idea. We have to follow that, no question about it. But there are unsolved issues yet with long-term storage and transportation over long distances about safety and costs. And that is why I think we need different technology options to come back to where my talk started. And I would like to share the idea we developed with researchers in this city, but as well with colleagues from outside Darmstadt, to use iron particles as carrier of renewable energies. Iron is free of carbon. It is storable. It is transportable with well-known technologies. We can release the energy which is stored in the iron by oxidation reactions without releasing any CO2, no greenhouse gases. And so the vision is shown here in this view graph. You see in the back windmills. That is the source where we generate in a sustainable way electricity. This electricity is stored in iron powder. It's like a battery, but at much larger scales. This iron powder is then transported to sites where we need this energy, and this is shown in the background here with this chemical production site, where we generate heat that can be used further on, as I will detail in a second. During this oxidation, of course, what you generate is an oxide. It's an iron oxide. It is rust, quite simple. You see that as Fa2O3 if everything went well and you extract all the energy contained in the iron. This can be collected from this oxidation reactors, and it can be brought back to those locations where we have excess energy from renewable sources. And this is the vision we are following in a project that's called Clean Circles, where we use iron as a carrier of renewable energies. And so a little more detail, starting with the storage. Renewable electricity is used to chemically reduce the iron oxides, either directly using the electricity in an electrochemical way or via the pathway of green hydrogen in a thermochemical way with synergies with this green steel production we are currently aiming for. Once reduced, you can say, the iron is then transported maybe a long distance and stored over long periods as well. It is brought to those locations where we need the energy. And there we just use air for high temperature oxidation reactions and generate heat. The heat can be used to drive a steam turbine, which operates then a generator to come up with CO2-free electricity. So we start with the upper left, renewable electricity, and we end in the lower right again with CO2-free electricity. Very important, to close the circle, we have to collect the iron oxides. Collect them from the reactors, bring them back to where the renewable electricity can be produced in the most cheap way. And that might be in Southern Europe, it might be in the MENA regions, it might be in the global south. So the idea is simple, chemical to thermal energy. However, why using iron? Why not another metal? The reason is, iron is one of the few metals that oxidize in the so-called type C mode. This means that the oxidation reactions, when you start with a particle, the oxidation reactions happen at the surface in a heterogeneous way, meaning that the oxides, the rust, forms like a shell, but it remains as a particle. And if you have an exhaust stream of a chemical reactor, particles, you can easily remove them with existing technologies like cyclones. So the iron is reused, ideally infinitely often. And that means closing the iron cycle is possible. With this idea, we can replace fossil fuels for, we call it high heat applications, particularly for processes where temperatures are above 750 degrees C. To use them to produce heat for industry, for example, melting materials in recycling industries, heating reactors in chemical industries, or driving turbines, as I said, producing steam, and that could be used to retrofit existing coal power plants. So the iron cycle offers the potential for CO2-free industrial processes, particularly there where electrification is not easily possible. Whenever we can, we should do it with electrification, but you can't do it for all the processes. And so let's go a little deeper in the idea to retrofit power plants that already exist. With that, the idea is, once you have, let's say, changed them for the operation, instead of using fossil coal, but use now iron particles that have been circulated in the way I described, with these kind of power plants that already exist, the idea is to compensate the volatility of the renewables, at least in this country. In other countries, relying strongly on coal now and in future, at least in the foreseeable future, having in mind that more than 1,000 coal power plants built these days, we need as well options to make them sustainable. And so the only option is to change the fuel. The fuel must be sustainable. With that, we would use existing infrastructure, which is a great benefit to have an easy market entry. The efficiency potential that we estimated based on simulations are up to 48%. You have to compare that to existing technology using hard coal, for example, which is 44%. So this is remarkably good. The iron cycle, including the transport, which comes on top, of course, you don't need to carry it only from the sites where you produce it, but you have to bring it back, has comparable efficiencies to gas turbines that, in the future at least, will be operated with green hydrogen, although this technology does not yet exist. You can't buy it yet. This comes along without any emissions of CO2 because there's no C included. So we don't emit any greenhouse gases. On the pollutant side as well, because there's no C atom included into the process, no CO, no soot, no hydrocarbons, and as well no sulfur oxides. So retrofitting existing coal-fired power plants, at least in our vision, in our idea and belief, has a huge potential not only for this country but as well worldwide. So with that, I would like to summarize, and I'll give you 3 take-home messages. So first, To make the transformation of the energy system successful, we need chemical energy carriers that are produced in a sustainable way from renewable sources. Second, the iron cycle, as described, has an enormous potential for CO2-free generation, both for electricity and industrial heat. And third, there's no free lunch. So we have to do extensive research and development to leverage the potential of the iron cycle, because there's no time left. We have to act now. Thank you very much.